The universe is a memory leak. Why physics requires you to exist. The star stutters, one heartbeat a flicker, then steadies like nothing happened. You freeze. Was it you or the sky? Here's the stake. If no information reaches us, did that star exist for us at all? Tonight we chase a hard claim with receipts. Reality stabilizes when it's copied, and that copy storm has a cost. Quantum Darwinism, Wheeler's participatory universe, and a coordination paradox that shouldn't work, but does. Who writes the record? Why do we agree on facts without a central server? And what fails when nobody's looking? To understand the flicker, we have to rewind to where reality gets written. The coordination paradox, shared reality without a server. You wake up, check your phone, look out the window, and step into a world that matches everyone else's story. The coffee mug sits on the counter for you and for me. Streetlights line up in the same order for a stranger across town. We treat this as obvious, but there's a brutal puzzle hiding in plain sight. How do billions of observers maintain a consistent world without a central authority rendering it for all of us at once? If you've ever played an online game with lag, you've seen the nightmare version. Two players act, the network stalls, then the server picks a winner and rewrites someone's memory of what just happened. Reality, at human scale, doesn't do that. We don't experience hard rollbacks. We don't get two incompatible histories stitched together by some cosmic admin. And yet, physics gives us every reason to expect dissync. Start local. Quantum mechanics says systems spread over possibilities and outcomes only become definite when information about them leaks into the world. That leaky record, photons bouncing off a mug, air molecules scattering from a table, gets copied out. Different observers sample different fractions of that environment and somehow get the same story. Meanwhile, relativity forbids instant coordination. No global clipboard, no universal present. Events that are simultaneous for me aren't for you. If there's no server and no instantaneous sync, why aren't contradictions everywhere? Here's where the paradox bites. If each of us only touches a small slice of the environment, we should expect local disagreements like that laggy game, because we're not comparing notes in real time. But we rarely disagree about simple macroscopic facts. The chair is where we all expect it. The building stands. The bus arrives. Most days, the world looks already decided before we arrive. To feel the stakes, follow a micro-story. A city electrician resets traffic lights after a power dip. Across town, a cyclist swears the crosswalk signal never changed. Meanwhile, a dashcam shows the correct sequence. 3 observers, 3 partial fragments. In a sane world, these fragments reconcile without a central broadcast. How? Redundancy. The environment isn't a passive screen, it's an active witness. Photons carry the same coarse details in millions of directions. Air molecules rehearse the same collisions again and again. Surfaces pick up scuffs, heat patterns, and tiny deformations. Those are copies, low fidelity in places, but numerous and overlapping. If many independent fragments agree, objectivity emerges as many observers, identical readout. You rely on this every time you cross a street. You don't need to talk to every driver. Headlights, engine noise, tire tracks, brake heat, redundant broadcasts tell you a car is there and coming fast. Your eye, a phone camera, and a random pedestrian can read different fragments and still land on the same fact. No server needed. The world copied the state everywhere. But if redundancy is the answer, why doesn't the system overload? 2 reasons. First, pointer stability. Some properties of systems, like position for big, clumsy objects, survive the chaos of environmental interactions. They're selected because the world keeps bumping into them without knocking them into delicate sewer positions. Second, irreversibility at scale. Once enough copies spread, erasing them would mean corralling countless degrees of freedom. Practically, nobody pays that bill. So the record sticks. Now remember relativity's constraint. No instant sync. That's fine because you don't need it. You need consistency within light cones and overlap across time. The copies don't have to reach everyone at once. They just have to spread far enough, fast enough, that later observers can agree. What looks like magic consensus is rolling local stabilization, multiplied by redundancy. There's another surprise. We are part of the broadcast network. Eyes, sensors, journals, file systems all add copies. A security camera doesn't just store pixels, it amplifies a local fact into magnetic domains and cloud backups. A lab notebook isn't just ink, it's a forked fragment other minds can read. Institutions, newsrooms, archives, courts are redundancy engines, cross-checking and preserving. Civilization is an environment with better storage. So where's the paradox now? It shifts. Shared reality works not because someone renders it globally, but because the environment continuously copies robust features into many independent channels, and those copies are cheap to read but expensive to erase. The server is replaced by a web of witnesses, and because the copies are everywhere, most of us most of the time agree. Still, there's a crack we can't ignore. Before the copies spread, facts can be parochial, tied to a lab bench, a memory buffer, a sensor that hasn't uploaded yet. That's where contradictions can appear and under controlled conditions do. Tabletop tests inspired by Wigner's friends show how, pre-broadcast, separate observers can carry incompatible stories that each pass local checks. The coordination paradox is solved not by perfection, but by timing and scale. The world doesn't need instant global truth. It needs enough local truth, copied widely enough soon enough, that histories align. This frames the rest of our journey. If redundancy stabilizes facts, what selects which facts survive? If the environment writes the record, why those variables and not others? And if every copy is a commitment, who pays the bill for a world that keeps itself in sync? Quantum Darwinism 101, Survival of the Fittest Facts. To see how redundancy actually picks winners, zoom in. A mug on a table doesn't just sit there. It's being pelted by photons from the lights and the sun, by air molecules jittering at room temperature, by tiny vibrations in the table legs. Every hit is a little interrogation. Where are you? Which way are you facing? Those interrogations don't pull out every microscopic detail. They favor certain variables that survive contact. In practice, position and orientation win. In the language of physics, they're pointer states, configurations that remain stable under the system's constant collisions with its environment. Here's the basic rule. In isolation, a quantum state evolves like a quiet symphony of possibilities. Add an environment and the symphony gets mic'd into the room. Phases, the delicate patterns that make interference possible, get entangled with countless outside degrees of freedom. Interference dies. That's decoherence. But it's not random. The system, environment coupling singles out a basis in which the state is least disturbed by monitoring. For dust grains in air or under light, that's position. For a current in a superconducting loop, it might be a circulating direction. Different systems, different winners, same selection logic. Selection is only step one. Objectivity needs copying. Quantum Darwinism says the environment doesn't just hammer a system into a stable basis. It also broadcasts records of those pointer states into many independent fragments. Think fragments like photons within this solid angle, vibrations in that tabletop mode, air molecules in this patch of room. If each fragment carries the same coarse-grained answer, mug here, handle there, then many observers can sample different fragments and agree without disturbing the mug. That's the birth of facts as we use the word. Many observers, identical readout. There's formal spine behind this idea. In spectrum broadcast structures, the joint state of a system and many environment pieces takes a special form. Disjoint fragments each correlate with the same pointer value, and those fragments can be read without disturbing the system or each other. That is objectivity by construction. Crucially, you don't need to scoop up the entire environment. A tiny fraction of fragments suffices to reconstruct the pointer state with high confidence. That's why glancing is enough. Make it concrete with a microstory. Sunlight spills through a kitchen window. A dust mote floats in the beam. To your eye, it's a shimmer. Under the hood, millions of optical modes are scattering off that mote every microsecond. Each scattered photon leaves with a phase shift and direction that depends on where the mode is. Across the room, a camera sensor that never talks to your retina records pixels that tell the same story. Meanwhile, air molecules carry minute momentum kicks encoding that position, and the tabletop picks up a whisper of vibration from the thermal bump of light. Independent fragments, same bit, position. The mote becomes a lighthouse of information, not by choice, but because the environment turned it into one. The timescales are ferocious. A micron-sized particle in air decoheres positions larger than a wavelength of visible light in about 10 seconds, functionally instant. Even in high vacuum with weak light, macroscopic positions lose interference long before human reflexes can intervene. The world looks classical not because quantum stuff is rare, but because copying is relentless where it matters. That relentless copying is why you don't see chairs in two places at once. Two clarifications keep us honest. First, decoherence doesn't invoke magical collapse. The global evolution is unitary. System plus environment become entangled. Locally, because the environment holds the phases hostage across countless inaccessible degrees of freedom, you can't recombine alternatives. For all practical purposes, a branch with a definite pointer value is what you get. Second, eyes aren't special. Any amplifier that turns microscopic differences into macroscopic records plays the role. A Geiger click, a CCD voltage pattern, scratch marks in mica from an alpha track. Agency is participation in the copy storm. Now tie this back to our coordination problem. We asked why we agree without a server. Quantum Darwinism gives the mechanism. Objectivity is a redundancy threshold. When enough independent fragments carry the same pointer information, overlapping observers, us cameras, dust, sample disjoint pieces and converge. No instant sync, no global clock, just many copies propagating at finite speed. Consensus is a property of coverage. Not every variable gets that treatment. Phases between macroscopically distinct positions aren't redundantly recorded. They're exactly what's washed out. Subtle joint properties that require cross-fragment comparisons can remain unbroadcast and therefore unobjective. That's the hidden selectivity. The environment promotes some observables to public facts and demotes others to fragile amplitudes. You're living in a universe where compression is policy. Store the stable, broadcastable bits. Let the rest stay implicit. This selectivity has a shadow cost. Copying isn't free. Once amplified beyond microscopic scales, records become hard to erase. The more redundancy, the more entropy committed to the environment. There's a ledger behind every consensus we enjoy. We've learned what survives contact and how the world spreads those survivors. Next, we'll meet the accountant who tallies the bill. The ledger Landauer, heat, and the cost of certainty. If copying makes facts, somebody pays the power bill. The accountant's name is Landauer, and the receipt is K times T times ln2 per bit. Translate that. At temperature T, erasing one bit releases at least kT ln2 of heat into the environment. Tiny per bit, about 3 times 10, minus 21 joules at room temperature, but not zero. Zero would make infinite precision free. Physics never offers that discount. Think about what a measurement really is. Before you read a system, evolution is reversible. Amplitudes slosh around without friction, phases carry future possibilities. Then you connect the system to an amplifier. A microscopic difference, an electron here, not there, triggers a cascade. An ion track, a voltage step, a latch flip. That cascade writes a record. To reuse the apparatus, you reset its memory to a standard ready state. Reset is logically irreversible. Many possible pasts mapped into ready. That logical irreversibility is where heat spills. Maxwell's demon learns it the hard way. He can sort fast from slow, but to clean his notebook he must pay at least kT ln2 per bit. The second law doesn't budge. This isn't just a clever argument from 1961. Engineers have chased the bound in real devices. Nanoscale magnetic memories, flipped slowly with careful protocols, dissipate energy close to the Landauer limit. They never beat it. They asymptote toward it when they run near-reversible cycles. That's the flaw modern experiments keep finding when they try to erase information without waste. Logical irreversibility demands entropy somewhere. Energy is the usual currency, but theory even shows other conserved quantities can bear the cost in exotic setups. The principle stays: to forget is to pay. Now look at objectivity through this ledger. Quantum Darwinism told us facts are redundantly recorded across many environment fragments: photons, phonons, domains, files. Redundancy is what lets you read the same bit from different places without coordination. But every extra copy increases the number of degrees of freedom you'd have to corral to erase the record. Stop imagining a single notebook. Imagine a rain of scattered photons, warmed air, flipped transistors, replicated backups. You don't just delete a file, you would need to reset a countryside. In practice, nobody has that control or that patience. Irreversibility becomes policy. Microstory. A detector runs overnight. Every event is cascaded into a voltage trace, turned into numbers on an SSD, mirrored to a RAID, synced to cloud storage. In the morning, a calibration error is found. The team deletes the files. The room does cool. They only remove directory pointers. True erasure, flipping each cell back to a ready state, would dump heat. Multiply by laboratories, telescopes, factories, phones, server farms. The faint thermodynamic glow of certainty is everywhere. So how does nature avoid boiling itself? Strategy. Reversible dynamics are cheap. Schrödinger is a miser. Classical Hamiltonian flow conserves phase space volume. The cosmos leans hard on reversible evolution until something must be committed. It defers finality. It compresses detail with symmetries and conservation laws. It caches. Once there's enough redundancy, extra copies can piggyback on existing broadcasts instead of spinning new amplifiers. In software terms, lazy evaluation. In physics terms, unitary evolution until an amplifier stamps a mark. There's a second budget to respect: storage. Holographic whispers say entropy, the maximum number of distinct internal states, scales with boundary area, not volume. Black holes taught that lesson with Bekenstein's bound and Hawking's temperature. If surfaces count and volumes emerge, there's a quota on how much distinct, recoverable detail fits in a causal patch. Try to overspecify a region. Track every microjitter explicitly, and gravity or thermodynamics will answer. Collapse it or smear it into heat. Bring it back to desks and sidewalks. Your laptop throttles because logical operations dissipate energy. Switching bits warm silicon and fans must remove that heat. Your brain forgets because maintaining high-fidelity synaptic states and replay paths costs metabolic energy. Sleep is garbage collection under constraint. Cameras meet shot noise floors. Quantum processors juggle a trade-off. Keep coherence cheap, reversible, or read out a result expensive, irreversible. Everywhere the same rule. Be selective about what becomes a stable record. This turns consensus from miracle to budgeted policy. The world spends bits to stabilize robust, useful variables, pointer states, across many channels. Observers and institutions amplify those choices. The bill shows up as heat pulses, mechanical wear, entropy increases. Where the cost is low and benefits high, facts proliferate. Where costs are high and benefits thin, alternatives stay uncommitted, floating as amplitudes until an amplifier makes the call. Timing matters. Copies propagate at light speed, operations are bound by available energy. Latency protects us from contradictions by spacing commitments in time and space. You don't need a global server, you need a ledger that respects budgets. Within light cones, redundancy can grow. Across them, merging weights. Outside horizons, records can't be fetched, so the ledger defers. One last twist. Erasure isn't evil, it's how systems recycle. But every reset is a little exhale of heat. That's why the environment is a palimpsest, not a pristine canvas. New records are written on top of a warm, noisy background shaped by old choices. If meaning rides on redundancy, then responsibility rides on what we choose to copy. You can burn energy on spectacle, or spend it on standards, archives, and open data that others can reread. In a paper-bit universe, that's how truth travels without frying the planet. So the accountant's verdict isn't gloomy, it's clarifying. Facts have a price. Copying stabilizes reality, but certainty is never free. The next constraint isn't thermal, it's geometric. If updates need time to spread, what sets the pace of truth? Latency of reality, light cones and bandwidth. If copying makes facts, time sets the rules. Nothing updates everywhere at once. The universe parcels truth inside light cones, and the speed of light is the scheduler. That number isn't trivia about photons. It's a budget constraint for causality. Any record that will matter to you has to travel to you along a path that never outruns light. No path, no update, no fact you can cache. Draw your life as a cone opening forward through time. Inside that cone, signals you send can reach. Outside, they can't. Flip it backward and you see what could have reached you by now. The overlap where cones meet is where consensus forms. You don't need instant sync. You need enough overlap soon enough that separate ledgers merge without contradiction. It's a rolling commit, not a global render. Latency isn't just speed, it's rate. Locally, there's a cap on how fast any system can tick through distinguishable states. Tie that to energy above the ground state and you get a clock bound. More energy, faster ticks. Less, slower. Pair that with finite temperature and Landauer's erase bill and you have a daily truth. You can't compute, copy, and reset at infinite frame rate. Physics throttles reality's clock. Here, S where latency saves you from paradox. Imagine two labs far apart, probing a system whose records haven't propagated. They can write different local stories without breaking physics, because neither can use those differences to signal the other faster than light. Contradictions can brew in isolated buffers. They resolve only when light cones overlap and broadcasts meet. Then redundancy negotiates the final story. Not perfect, but enough. Microstory. A team runs a distributed plasma simulation. To hide delay, each node guesses neighbors' next states. It screams until two guesses collide. Different regions believe different histories. The run blows up. The fix: enforce finite light cones. Finalize only inside a node's causal neighborhood. Wait for messages from beyond before committing. Slower on paper, stable in practice. Relativity reads like that fix written into spacetime. Scale to the sky. Cosmology hands you two edges people mix up: the particle horizon and the event horizon. The particle horizon is the farthest light that could have reached us since the hot beginning. It grows as new photons arrive from just beyond yesterday's limit. The event horizon is colder. In an accelerating universe, there's a boundary beyond which even light aimed our way now will never reach us. For our ledger, that's a permanent, unreachable flag. Facts beyond cannot be copied into our patch, not ever. This architecture explains why no server reality doesn't collapse. Consensus forms in patches, propagates outward, and stitches with neighbors when cones meet. Stability rides on simple invariants piggybacking on light. Energy, momentum, spectral lines, acoustic peaks in the microwave sky. Those are cheap, robust messages that keep distant regions compatible without heavy synchronization. The network runs lean. Latency also protects objectivity from being overwritten. If records could outrun light, different frames could disagree on which happened first, and you get race conditions in physics. Two writes to the same world line with no consistent order. The speed of light forbids that. It enforces a schedule every observer can reconcile, even if their slices of now differ. The universe trades immediacy for consistency. Add bandwidth. Every channel has a capacity. Shannon told us noise eats rate. You compensate with energy, coding, and time. Nature does the same. Bright sources push more photons, but shot noise still bites. Detectors integrate longer to raise confidence. Redundancy accumulates gradually, and only when enough bits pile up does a fact become robust. Objectivity has a startup time. Holographic hints make this tighter. Storage quotas scale with boundary area, not volume. Your causal patch carries a finite ledger. Try to stuff too many distinct bits into a region or demand too much update rate, and gravity answers with collapse or thermodynamics with heat. The safest policy is the one we already see. Compress, defer, and broadcast selectively. Keep the ledger thin. Human moment. A radio array hunts nanohertz gravitational waves by timing millisecond pulsars. They're listening for a correlated drift across many clocks, space itself ringing. Months pass. A hint appears. They don't declare victory. They extend baselines, cross-check noise, wait for more cycles. Latency forces patience. Proof accrues at light speed. So the picture sharpens. We don't need a central server. We need a mesh of finite clocks, bounded channels, and patient broadcasts. Within light cones, redundancy turns fragile amplitudes into stable records. Across cones, consistency emerges when messages finally meet. Outside horizons, facts may exist for someone else, but not for us. The ledger writes where signals can go, at the rate energy can afford.